Okay, so I've got a lot of material here, but I don't have a lot of audience, which means if you have questions, you can probably interrupt me. If you want me to slow down, you should definitely wave your hand and tell me to slow down. There's some material that I won't have time to go over, but it is in the slides. So you can be able to get the slides and look through that after the talk, or you can watch the video again, I suppose, after the talk, after the conference, I mean. And this is an introduction. So the first half is really quite introductory. If you already know OpenACC, then feel free to check your email for the next half an hour, and then there's a little bit more advanced material after that. And this is more or less the summary of the talk, the advanced stuff at the end, using the compilers, blah, 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 blah. And this is the architecture. This is the node architecture today that OpenACC targets. So the key points about the architecture are separate memory and a separate compute unit. So I call this the highly parallel unit, and this is the high performance unit, or the high speed unit, I should say. Faster clock, slower clocks, more parallelism, less parallelism, big memory, fast memory, high bandwidth memory. So those are the key components. Those components will survive beyond, and some numbers will change and some other things will change. But these are the key components of the node architecture, of a lot of different node architectures of the future. And if you look at the difference between that compute unit that was on your left and the compute unit that's on your right, so the high-speed cores and the highly parallel cores, what is the big difference between them? Well, so I'd be comparing today a CPU and a GPU, or basically any CPU versus any accelerator. The key features shown here, and the ones that are important, like faster clock on this side, more pipelining on this side, more instructions per clock issued on this side, but wider SIMD instructions, and more cores for some definition of core. My definition is a CUDA core is not a core. A CUDA core is a SIMD lane. Big cache, lots of branch prediction, a lot of out-of-order execution, none of that over there. So if you look on the side of the highly parallel part, the numbers in green are all the numbers having to do that need more parallelism from the application. So you get your performance over here from parallelism, lots of parallelism. 2 orders of magnitude more parallelism than you need over here. Orders of magnitude decimal, not binary. So you need a lot of parallelism. You need to create that in your application and then expose that and make sure it gets exploited when you write and execute your program. So it's all about parallelism. And someone's going to say, well, what if you don't have a parallel application? Then don't run over there, because it's not going to run very fast. It doesn't matter how you write it. Okay, so simple Fortran example. I'm going to show this 2 ways, and all I got is some data and a call and a routine and then a loop inside the routine. The body doesn't matter here. And you could do this in CUDA Fortran, and I'm not going to show a heck of a lot of CUDA Fortran. I think just this one slide and the next. And CUDA Fortran, you would allocate some device data, copy data as necessary between host and device, launch the kernel, copy the data back, and deallocate it. And then on the device, you would write the kernel itself. And you can do that today. This is basically what you would do today in most CUDA programs as well. And so the body of the loop turns into the body of your kernel. Well, if the body of your loop turns into the body of your kernel, why can't the compiler do that for you? Well, okay, that's what OpenACC is started out being about. So what's OpenACC? Directive-based programming. It's intended to be syntactically and semantically similar to OpenMP. The intent from the beginning was it would eventually become part of OpenMP. There's tension there, as you probably know. That will continue for a while. Stuff will happen. Some parts, OpenMP has the device directive. This is OpenACC. There's movement, there's design being moved from OpenACC into OpenMP, and some going the other way. I mean, OpenACC, we made some mistakes come tomorrow to my talk about OpenACC 2.5, and you'll learn about one of the mistakes we made, so we're inheriting some of the decisions made from OpenMP. And the intent was, with directives, it improves maintainability because you only have to deal with one piece of code. Improves portability because at least it runs on the host as well. And scalability. And the scalability, well, this is a good question, but next week, either next week or the week after, there's an article coming out in HPC Wire written by, well, me, about parallel loops. And the whole point is we need more parallelism. We need to expose parallelism. I need to say this really is a parallel loop so I can use as much parallelism on the hardware as possible. And that's something that OpenACC has and OpenMP does not. That's not the only thing, but that is an important one. So here's that same example written with OpenACC directives. So instead of CUDA Fortran, for instance, you have data management and compute management. Those are the two key characteristics of an OpenACC program today. I'm going to move data from the host to the device and bring the results back, which means allocating and copying data. So this is a data construct. During the lifetime of the construct, that's the data region. That's the dynamic range of the construct. During the data region, there's two copies of those arrays, A and B, the host copy and the device copy. And they can become incoherent in the computer science sense, which means they don't match. Because if you're changing values over on this side, they don't get updated on the CPU side until you move the data back. And if you change data on both sides, well, then you probably have a bug, but sometimes people want to do that on purpose. And then the compute management, well, that's showing here parallel loop. We also have kernels. I'll go over some of that a little bit here, but it's more like OpenMP, where you're defining your parallelism. Some details to come. Okay, so the data directives. Let's just talk about data management. This is the fun part that's not fun. The fun part is getting things to run fast, but this is the part that's slow. It's particularly slow today because that link between, if you remember the architecture, the CPU and the accelerator on your right is a PCI Express bus, which is a very good I/O bus and a really, really bad memory bus. It's order of magnitude slower than memory, so you need to minimize the volume and frequency of data moving across that bus as much as possible. So data management is going to be, for most programs, the #1 performance limiter, the #1 characteristic that's going to limit how much performance you get out of your program. So you're going to have to pay attention to it at some point until we get to other systems in the distant future, but we'll come to that later. So data management, you've got the data construct. So this is a structured construct with a begin and an end, and just like any other structured construct, the begin and the end has to be in the same routine. And at the top, you can do copy, copy in, copy out, and create. Those are your data clauses that will say allocate the data and copy it into the device, or allocate the data and copy it out at the end, or allocate the data and do both, copy in and copy out. Or if it's a temp array, you would just say create the data, because the data on the host doesn't matter. And Fortran being a higher level programming language, unlike some other languages being discussed in other rooms, the arrays actually have shape information with them. So you just give the array name and the whole array goes over. What if you just want to do the subarray? Well, you can allocate and move a subarray, but you're going to have to allocate and move a contiguous subarray. So it can be the whole first dimension, part of the second dimension, for instance. And then that data is live on the device during the whole execution, including during updates, routines that get updated. All right, then you have update directives. So update self and update device. You can also say update host, which makes more sense, but there are reasons to call it update self that I'm not going to get into today, but I'll be glad to if you want to talk about it afterwards. So this, when it's running on the host, will take data from the device and copy it in. This takes data from the host and copies it back. So for instance, if you need to do a Halo exchange, you might need to copy data back and then do your MPI exchange and copy data across. And someone's going to ask, well, what about GPU direct? And yeah, you can do that too. I'm not showing that here, but this is an example. And so you can update parts of arrays here. You can specify sections. They don't have to be contiguous sections. There's performance disadvantages and advantages. If you allocate non-contiguous sections, you're moving fewer data, but it takes more moves. So there it is. And then there is enter data and exit data. So these are like, enter data is like the top of a data construct, and exit data is like the bottom of a data construct, but it's unstructured. So you can put this in an init routine and put this in a finalization routine and copy some data in, and then it stays there until you're done and you copy it back out. So we found that to be, from user feedback, very important, because some people have different, their programs are not as perfectly structured as we initially thought. Okay, so otherwise it's more or less the same as before. Then the compute region. So the one that you want to focus on when you're starting out, if you're just starting out, is ACC parallel loop. That says, for instance, it says, this is a parallel loop. Run the iterations in parallel as fast as you possibly can. And there's a lot of clauses you can put on there. You can add data clauses. I talked about copy, copy, and copy out. You can put those here. You can also put present. Present tells the compiler the data had better be there, and so it checks at runtime. If the data is not on the device, then you get a runtime error. And if you're relating this to CUDA, then the body of the loop turns into the body of a kernel, and it launches that kernel on the device with a launch configuration, so the grid and the thread block, based on gangs, workers, and vectors. I don't like the name. Nobody likes the name, but it's the best we could come up with at the time. So think of gang corresponds roughly to an OpenMP thread. Vector corresponds roughly to a SIMD lane. Worker, and if you're beginning out, I'd advise you ignore worker. Just don't even think about worker. Just think about gangs and vectors. That's parallel and vector computation. We all know what that is. If you want to do fine tuning, then you might want an extra level of parallelism. That's your worker level. And so if you have nested loops, for instance, you might want to define this inner loop is a parallel loop. Do this on the vector dimension. Why do you want to do this one on the vector dimension and not the other? Well, for the same reason you would want to do one loop in vector mode on a cray. If you all remember crays, some of you have grayer hair than others. Why you'd want one loop to run on a cray versus the other? Why would you want one loop to run in SIMD mode on an x86? Because the stride is 1. You want stride 1 operations. The CUDA guys will tell you there are no vectors in CUDA, and that's a great advantage. And my response is the worst thing about CUDA is there are no vectors in CUDA. Actually, there are vectors in CUDA, and I can't write them. Because to get performance, I need stride 1 operations. I need non-divergent execution. Looks like a vector to me. If it looks like a duck and quacks like a duck, it's a duck. So inner loop or stride 1 loop, I want to run in vector mode. The non-stride 1 loop, I want to run across my gangs. Now then there's this kernels operation. So the key difference between kernels and parallel, and this is yeah, you might ask for historical reasons why we have both. I'm not going to get into that. But be glad to talk about that over a beer. You owe me a beer. So why do we have both parallel and kernels? So it's for historical reasons. The parallel loop works more or less exactly like the OpenMP parallel do, or parallel for if you're a C programmer. It says, launch this thing in parallel, and the scope is the loop. And I'm guaranteeing that, in fact, there is parallelism there. And if you just OMP parallel, it actually starts executing redundantly on each thread. ACC parallel, if you have code between parallel and the loop, then it's just like that. It starts executing things redundantly. Kernels loop, it says, I want this to run in parallel, but I want the compiler to do the dependence analysis. So it really only works if there's no function calls, for instance. It doesn't work when there's procedure, because I can't do dependence analysis across procedures. But it works pretty well for Fortran array assignments, okay, or for relatively simple operations. So we use kernels, and in fact, you don't need any other thing at all. You can just say kernels end kernels, and the compiler will analyze each of the loops and try to find the parallelism. When we're first starting out with programs, sometimes we just do that. I'm not advocating necessarily that's what you want to do or need to do, but I'm just saying it's something that we do. All right, so in these loops, you can have reductions. Just like OpenMP, you have a reduction clause. You define the operator and the variable question. So he's asking, that's a long question. And the short answer is because the penalty of making a bad decision is too high to let the compiler determine that. Bad decision on what to run on the device versus on the, we tried that. Okay, so you have a bunch of operators, and the variable here, this right now has to be a scalar. We don't have array reductions. That may come depending on what we have there. You have the collapse clause, which works just like the collapse clause in OpenMP. And so then it has nested loops, and then it runs that, and okay, fine. And now remember, why is the collapse clause good? It's going to be even more important for these highly parallel devices because you need more parallelism. Where's the parallelism coming from? Well, there's only two sources of scalable parallelism in a program, recursion and loops. Here we're focusing on loops. Nested loops, that's even better. Nested parallel loops, that's perfect. That's what you want, is a lot of parallelism. Okay, we talked about the kernel's construct, and there is, I'm supposed to talk about auto versus independent. Oh, I'm sorry, there it is. Here's independent. So the compiler will do the analysis and find the parallelism, and if it doesn't, and you think it should, in a kernel's construct, you can add the independent clause on a loop. You can add it on in a parallel construct, but as you'll hear in a moment, it's implicit. So the default in a kernel's construct is every loop the compiler will auto-determine. Is this loop running in parallel? And if the iterations are independent, then it'll try to run it in parallel. But you can tell the compiler this is independent because that's an index array. It's a permutation array. Compiler could never determine that. But you can tell it that the iterations are independent, and so go ahead and run it in parallel. In a parallel construct, oops, that's a bad example. In a parallel construct, the default is, if I say ACC loop, I'm telling the compiler those are independent iterations, run those in parallel. If I want the compiler in a parallel construct to do the analysis, add the auto clause. None of you will ever do that, so don't bother remembering that one. You have private and reduction. Okay, private, more or less just like OpenMP private. And here it works as you would expect. Okay, fine. We have atomic updates, atomic read, atomic write, atomic capture. Again, matches the OpenMP behavior. And as far as synchronizations go, there aren't many synchronizations in OpenACC, not nearly as rich as the synchronizations in OpenMP. But remember, we're looking at scalable parallelism. Synchronization is inherently not scalable. So, but atomics are. You can do atomics and get scalable performance out of that. Now, we already looked at update. I don't know why I have that in again. Question? That is true. So the question is, can you do an atomic operation and have 4 things in a row? No, it's atomic per operation. For that, you would really want something, what you really want is a transaction. Yeah, and we don't have that. You want to do like an atomic update of a struct of a. Right. That's a fair question. No, we don't have that. All right. Using the compiler. So PG Fortran is the name of the compiler. It has some other aliases, but that's the one we'll use here. There are 3 important flags, -ACC, -TA, and -MInfo. So ACC is the analog to our MP flag. It enables OpenACC directives. TA is the analog to our TP flag. TP is target processor. TA is target accelerator. And we have other options. We have options Tesla, Radeon, and host. So today we support Tesla and Radeon. Radeon, we have more features for Tesla than for Radeon because OpenCL doesn't have things like a linker, so you don't have separate compilation. Those things will be coming. If you just say -TA, it implies -ACC. You don't have to specify them both. The default is TA equals Tesla, host. What that means is at runtime, the runtime will auto-detect, do I have a Tesla accelerator? If I do, I'll use it. If I don't, I'll just run everything on the host. Today, when you say TA equals host, it generates a host version, or Tesla, host, it generates a host version, but that version is sequential. It's not a parallel version. And that's my #1 goal for this year. So I'll come to supercomputing, see if I get my bonus to run the OpenACC parallel across my multi-core host, or, as you'll see, other things as well. And then the MInfo, and I have an example of the MInfo messages. And we encourage you to enable that and to look at the MInfo messages because it tells you a lot of interesting things. Anyway, so you compile it and you get an A.out. It's just an A.out. There's no extra files lying around. You compile it to an object file. It's just an object file. You can put them in libraries. They all just work. It's just like, well, it's just like CUDA. And it just works. You can have sub-options to the Tesla option to the -TA flag. And some of the more useful ones that you can specify compute capability. So the default compute capability, if you say NVCC, is still SM10, which is good luck finding one of those. The default compute we don't even support SM10. We've given up on that one. So the compute capability for our compiler is you compile for the Fermi and the Kepler and the K20. Because you can do some extra things to generate specific code for the K20 versus the Kepler K10. You can specify, say you're compiling for just one particular system, and you know what it has, you can specify compute capability. 3.5 would be your Kepler K20. As with NVCC, you can generate relocatable device code or not. Our default is generate code that's relocatable so you can link across files. That's different than NVCC. There are some advantages to turning that off. One of the advantages is if you don't know if you're generating a library and you don't know if the person using the library will be linking relocatable code, you might want to build your library with no RDC. And there are some small performance advantages you get. So if you're after every last bit of performance, you can try enabling no relocatable device code. If you're looking for exact comparison between host and device, well, for floating point code, we all know the floating arithmetic reassociation is not necessarily computational reassociation. So, and where these things fall apart are, well, reductions. We all know about that. But also a fused mul add. So both CPUs and GPUs have fused multiply add instructions. And the difference with a fused multiply add is we do the multiply and then send that result to the add. It does not normalize the result between the multiply and the add. So you're actually carrying more precision. So it's a better answer. But it doesn't matter. It's a different answer. And you're looking for bit exactness. So you might need to disable FMA. There's also an FMA flag for the host. If you disable it on the host, it gets disabled by default on the device. You can specify your toolkit version in, I'm showing my age here because next month we're going to, our default today is CUDA 6.0. With 15.4, our default will be CUDA 6.5. We'll be delivering the CUDA 7.0 toolkit as well. And you may ask, why is your default always one behind NVCC? Well, because our customers are usually one behind NVCC. Titan is still on CUDA 5.5 for Pete's sake. And there's some other things. You can keep the GPU file. Now, if you look at the GPU file, it's going to be LLVMIR. It's not going to do you a heck of a lot of good. There's another flag. You can say no LLVM, sub-option, no LLVM, and then it'll save the corresponding CUDA C. Good luck reading that. It's assembly language written in C. And you can also just add -help, and it'll give you the help for whatever options you have on the command line. And then MInfo, and I encourage you to turn on MInfo equals Excel, and it tells you more or less what it's trying to do. So it'll tell you things like, it gives you the launch configuration. So this was compiling one of those loops we had in before. In this case, it chooses vector 256, so that's going to be a thread block of size 256. The gang is going to be across the grid. It tells you whether the data is being copied in or where it's being copied in and copied out, and so on. Okay, some other hints here. And I'm going to check my time schedule. I'm good. Okay, PJACCNotify. So this is an environment variable. It's a PGI thing, not an OpenACC thing. Everything I've shown you so far, except for the command line flags. The language stuff is all OpenACC and should port. It's all OpenACC 2.0, should port across all the different implementations. Now, you can set PJACCNotify. It's actually a bit mask. There's 5 bits, 1, 2, 4, 8, 16. 2, 4, 8, 16, yeah. And the interesting ones are bit 1 and 2. And bit 1 tells you when a kernel gets launched. It gives you information about that kernel. And bit 2 tells you about data uploads and downloads, so you can trace more or less where things are happening if you're trying to do performance analysis or just see whether your program is working at all. We also have PJACCTime, And this enables our internal data collection or performance collection routine, which uses the OpenACC profile tools interface that I think is being talked about in the next talk. But we just have something that's very simple. It collects information about how much time is being spent doing data transfers, how much time is being spent doing kernel launches, and it summarizes all that like a profile. And it's a first level. You can also use CUDA-Prof or NVProf, and you can use other tools that work as well. When it runs, it's just a CUDA program that runs, and you should be able to use any tools that use that. Okay, that's all the more or less introductory material, and I'm going to go through some other advanced stuff. Nothing really advanced, but some stuff that you'll be running into if you're a real Fortran programmer doing real OpenACC programming. All right, host data. So the point with host data is I've got a function call to a routine, and that routine needs CUDA device addresses. So like I'm using GPU direct, I need to send the CUDA address to MPI. How do I do that? Well, host data, use device A, which says inside here, wherever I see A, replace that by the device address for A. And that works really well. There was a talk yesterday where they did exactly this for exactly this reason. And, right. Multiple threads. So this is multiple OpenMP threads. Does OpenACC work in an environment where you have OpenACC inside OpenMP threads? Yes. Now here I am talking about the PGI implementation. This is not specified, I believe, in the OpenACC. But the way we've implemented this, I can have parallel do and then ACC parallel loop inside that. So what happens is I've got multiple threads. If they're sharing the same device, which is this slide, then they're going to share the same context on the device. They're going to share data on the device. So if they're sharing data on the device, then you can have race conditions. You can have other conflicts between data on the device and data on the host. But most of the time, it works just fine. We don't support OpenMP parallel and ACC parallel on the same loop. Sorry. Or OpenMP do and ACC loop on the same loop. All right. To do, oh sure, because yes, because the question was, what's the advantage of doing OpenACC inside OpenMP? And the bigger advantage is this next slide, which is multiple devices. Okay, so there are 3 ways to handle multiple devices that are supported. The easiest and the way that's most natural is I have 2 MPI ranks or some number of MPI ranks and have each MPI process choose a device. For that, we use the ACC set device num. So you say, what device am I going to use? Have each rank choose a device and then use that device. And because they're separate processes, they don't share data. They won't share context on the device. They'll each run independently. Of course, if you have more MPI ranks than you have GPUs, some of them will share a device, and you can run out of memory because, as you know, GPUs, that's physical memory. It's not paged. You can use OpenMP threads and have each thread choose a device. And the ones that get separate devices, okay, they'll have separate contexts and they'll be running independently. If you have 2 of them happen to run in on the same device, they'll conflict with each other both in terms of data usage, and they might share memory on the device, all that as before. Now you can, in a single thread, switch between devices. You can do your set device num and do some stuff, and do some other set device num and do some other stuff. That's really hard. That's really, really hard. Unless someone else makes it easy. We have made it work, but it's a challenge just keeping track which data is on which device, because some data, like the read-only data, maybe you want that on both devices. So you have to move it twice. It's really hard. Okay, some other stuff. What about module data? I want to put module data on the device. So we have global declares, declare create. We also have declare copy in, but declare create is the one I'll talk about here. So for things like scalars and other static data, when you say declare create, what it will do is, well, you have your host data, it will declare static data on the device as well. Now, you still have to keep them coherent. It's separate data over there. So you're going to have to, if you updated one side, you're going to have to do update clauses to update the other side. There's some special behavior for allocatables. This is something PGI has implemented and is now will be in the next version of the specification. If you have a Fortran allocatable, and you say ACC declare create, then when I allocate that array, it'll allocate both the host and the device copies. Okay, 2 copies. They're not coherent. When you assign to one, you want to do the update to get the data to the other side, but allocate and free will allocate both of them for you automatically. Procedures. So this, when you did OpenACC 1.0, this was the biggest missing piece. You couldn't do a procedure call because you couldn't compile a procedure for the device. All right, well, now you can. It's not perfect yet, but it's getting closer. So ACC routine says inside the procedure, compile this routine for the device. It's going to also compile it for the host, but it'll compile it for the device. And I specify a level of parallelism. This is the parallelism inside the routine. Is there gang parallelism inside? Then I have to specify gang on the device. There's no gang parallelism, but there's vector parallelism. I specify vector here. And if it's just a sequential routine, as most of them will be, you specify SEQ, sequential routine. Right, and then when I call this routine has gang parallelism. So when I call this routine, it'll be inside ACC parallel, not inside a gang loop, because this is the gang loop. So I'd call this outside the gang loop. The call will happen redundantly by each gang. Each gang will do some subset of these iterations and then return back to the host. So OpenMP has more or less the same thing. This is what they call an orphan loop construct because there's no parallel or kernels around this. OpenMP has the same thing. The differences between OpenMP and OpenACC here are I have to annotate which routines to compile for the device. OpenMP more or less has the same thing for their target directives, but the classical OpenMP, I'm compiling every routine for the host, and all I have is the host, so I didn't need that. The other thing OpenMP has, OpenACC does not, is at the end of a gang loop, in OpenMP there's a barrier. Okay, for OpenMP parallel do, there's a barrier there. OpenACC, there are no barriers across gang loops. There are barriers at the end of vector and worker loops if you use worker, but not across gang loops. And the reason for not having that is these highly parallel devices, thread creation is cheap. You just create a lot of threads. You launch a lot of gangs. Not all the gangs are even live at one time. You can't do a gang barrier if you don't have all the gangs there. The gang's not all here. I just coined that. Okay, so there's no barriers at the end of a gang loop. So there's no reduction on a gang loop inside a routine because you need a barrier to do that, to know when everybody's done to complete your reduction. All right. And I'm winding down here, asynchronous operations. And this can be very important if any of you went to the talk today about NICAM. They talked about how they did all this work using Fortran and getting everything working, and then getting asynchronous operations was really important for performance because then you can overlap data movement with computation. And some of the computation you're overlapping is setting up the next kernel launch, for instance. There's a certain amount of time there, and so you want to overlap as much as possible. What you think about is the device has queues, and we're shoving data into those queues. Multiple queues is okay, but you don't know what order things are happening between multiple queues. And you can synchronize. Okay, async says push this onto a queue. This says wait for Q1 to finish. Okay, you don't have to have an argument there. There is a default queue. And the difference between this slide and this one is that loop construct will get launched onto Q1 before Q2 finishes, but it will synchronize with whatever's at the end of Q2 at that point. And then the host continues on. So you can have both wait and async, and you can have a wait with an async clause, so that will put a wait on that async queue. Okay. It's great. This is really important stuff, too. Okay, derived types. Derived types do work, but they're a pain. And it's not perfect, and it won't be until we get to sometime in the distant future, or as you'll see, unified memory. So the point being, what you want is you need a drive type with an array member. That's the important one. And so you have the drive type itself and then the members itself, and you need to move both of those over there and make sure the drive type on the device points to the device copy, not the host copy. And so this is the pain part. You have to move the drive type over there and then move the members over there. And in the PGI implementation, this is not part of the specification, but in the PGI implementation, when you move the member, if the drive type itself is on the device, it will update the pointer on the device as well. And so that's the only way to make it work that we have today. I'm sorry, but there it is. We know this is a big hole, and if you have an array of drive type that have array members, okay, that's a real pain. But we're working very actively on that. Come to the talk tomorrow about the future. And the last thing I'm going to talk about is managed memory. I mean, CUDA's got this unified memory. Can we just use that? And almost. So we have this option. It requires a separate download. And you can enables the CUDA Tesla manage, and then all the allocates, because it only works for dynamic memory. So all the allocatable arrays will get allocated in the managed memory space, but you're limited to the size of the GPU memory, because managed means it allocates it on both sides. So you're limited to whatever the size of your GPU memory is. If you're doing asynchronous operations, you can have where if the host is accessing data while the kernel is live, you can get seg faults. There are some other issues but it's a good place to start. If you're first starting a program, this is now our initial approach is we turn on T equals Tesla manage, and then we get the compute working, and then we start working on data for performance. And last bit I think here is interoperability, and I'm almost out of time, so I'm just going to really flip through this. You can use CUDA Fortran device data in OpenACC constructs. You can use OpenACC data inside CUDA calls to CUDA constructs. Here, because the compiler knows that this is, in fact, a device attribute, argument with device attribute, it knows that it should use the device copy for the data there. And you can call CUDA device routines from inside OpenACC regions. So this only works in CUDA Fortran. You can do it with CUDA C as well, but you have to write an interface block. Common errors. There's some on the left there, and I won't go over much of them. We talked about reduction errors. The biggest ones would be stale data or accessing data out of bounds. And these are mostly programmer errors. We do not have a good set of tools to find all of these. CUDA memcheck is pretty good. Find some of these. That's pretty good. It does not help you with stale data, for instance. All right. And this is the summary. So I'm done. I'll take some questions if there are any more.
Does anybody have any questions? Yes.
All right. So a couple slides, like 2 slides ago, one more back. All right. So is this in CUDA Fortran, or is that you demonstrated OpenACC?
Okay. So this is an ACC data region.
Oh, okay. So you don't have
calling
to do the host data.
This is a CUDA Fortran call.
Okay.
Okay. Now, the CUDA Fortran call, this could, if you had an interface block, this could be written in CUDA C, and you just have the interface block that tells you how to do that call. Or it could be in a CUDA Fortran, like in a module, and it would already have that interface.
Sorry, I had one. And the other question I had was when you were trying to explain the more complicated asynchronous, where you had the 2 streams. Would you mind walking through what you had said again? I wasn't able to follow. What
here?
Yeah, I can't figure out exactly what
okay, so think of
will be.
I have 2 queues, my visual, all right? And he lines up here. I'm pushing stuff on the queue. So there's a guy standing here, and there's a guy standing here, and I push something over here, and I push something over here. And I say, okay, I want to launch a 3rd thing on this queue. I want it to run after both these guys are done. And I don't want the host to wait. Right? One thing to do is just have the host wait until they're both finished, and then launch this, put this guy on the queue. But I don't want to have the host wait. So what I'm going to do is I'm going to put on this queue, wait for that guy to finish. And then this thing here. Okay, so these things will kind of flutter down. Then the wait gets here and it says, well, is he done? And if not, I wait until he's done. And then, okay, then let the next one go on.
But meanwhile, the CPU is able to continue.
And all that time, the CPU has gone on to do other things. Right? The point is the CPU is not waiting. The queue has a wait on it. So that's done in the hardware on the device.
Any other questions? Go ahead.
Oh, I misinterpreted this. This is kind of, I got 10 minutes left. Here I was rushing. I got 10 minutes left.
So there is a separate compiler for CUDA-C, and also there are separate compilers for OpenMP-C, right?
So CUDA-C is a separate compiler. That's NVCC.
Is it the same for Fortran, CUDA Fortran, and also OpenCC Fortran?
Yes, the PG Fortran does both CUDA Fortran and OpenACC. If you have the suffix .cuf, that's CUDA Fortran, or the -m CUDA flag will enable the CUDA Fortran extensions. And you can include both CUDA Fortran and OpenACC in the same file, in the same function, in the same loop. One up front.
When I tried using the PGA compiler 2 years ago, so there was a performance of maybe 5x when I would use simple loops, and when I write it in pure CUDA, I would get a performance of, compared to one CPU, of about 150. Is there any with
what's
all those
wrong with your compiler?
Yeah, I know. With those new directives you showed at the beginning, is there any gain in performance that you have approximately?
Okay, so there's a couple things that could be going on here, and I'm not going to say that you played any tricks, and it's true. The general question is, how good is performance relative to native CUDA? All right, and okay, I'm writing a compiler. The compiler is as smart as we can make it, but it's not as smart as you. On the other hand, the compiler is tireless. You are not. If you want the highest performance, you should go to the lowest level that you need to get that performance. Why aren't you writing in assembly language? You want the highest performance? Why do you trust compilers at all? Well, because that's not a productive use of your time. Okay, now when you're rewriting the code in CUDA, you're doing a couple things. One of them is you're rethinking your algorithm. You're saying, I need a lot more parallelism, so maybe I'll, instead of writing it as two loops, I'll do it all together in one kernel operation. Maybe I'll change from, I don't know, I'm not an algorithms person, so I don't know what I'm talking about here, but I'll change from one structure to another. Maybe I'll change the data structure. Compilers, we don't see the algorithm. We don't see the application. All we see is the program. We just have to compile the program the way you wrote it. So it is true. You're never going to get exactly as good a performance as you would if you wrote a highly tuned CUDA program. It's just not going to happen. It's the same as assembly language. We're not going to do as good as a good assembly language programmer, and we make no bones about that. If you have a library you can call, you should use a library, because those guys are tireless to a point as well. What we have found that if you take the OpenACC program and the corresponding simple translation into CUDA, we match that pretty well. We think we match that pretty well, but we can't change data structure layouts. There are some issues with data structure layouts. That's come to the talk tomorrow. We can talk about that, about and beyond part, right? That was one of the things at NICAM they had to do, is change the data structure layout because it was laid out for caches, not for high parallelism. We can't take separate loops and just mash them together. We don't have the analysis to know when that's legal or profitable, for that matter. So, but we have shown where we can get very close to the native CUDA performance in many cases. A lot of times users will use, to get into their shared memory and things, and the compiler tries to do as much of that as it can, but it's not as good as you are. It's not really answering your question directly, and I'm whining a lot, but there it is. So caches and vectors, regardless of any, okay, if you go back to the architecture slide there, the CPU cache is huge, right? 20 megabytes, or sometimes even more. 20 megabytes when I was young was a disk. It was a Speed Queen disk. It was the size of a washing machine. And on the device side, the caches are tiny. It's like a megabyte. So you're not optimizing for caches so much. It's the difference in where this thing gets its performance. As I said, it gets its performance from parallelism. What's this thing? What I didn't show here is the three phases here. How do you make it faster? Well, faster clock, slower clock. Faster clock, sorry, we're done. It's never going to get any faster. The fastest CPU I ever saw was an IBM Power at 5 gigahertz. Some DSPs will run up to 10 gigahertz if they use some special technology. But no, sorry, that bullet is done. We're never going to see faster clocks. Sorry, no gallium arsenide. I don't believe in any of that. So we're done with the other two. Either more work per clock, and this guy has a lot of ways to get more work per clock, and this guy only has 2. More cores and SIMD width. More parallelism. This is trying to do more cores, more work per clock for a single thread, right? Heavy pipelines, a lot of multi-scalar operations. And then fewer stalls. So the stall is when the processor goes along and says, I have to wait for something. What can I do so I don't have to wait? What do you do? Big cache memory, so you're not waiting on memory. You know, I don't want to spend my transistors on cache. I want to spend my transistors on functional units. A lot of branch predictions. When I get to a branch, I don't have to wait to find out which direction to go. I'll just go both directions, or I'll select a direction. And if I'm wrong, okay, so I have to kill those instructions. But usually I'm right. So usually my branch prediction is good. I don't want to waste those transistors on branch prediction. I want to put those transistors into functional units. Out of order execution. So this instruction has to wait for that one, but I'll just issue the next one. And then continue on. And that takes a lot of control unit time. There's a lot of transistors, a lot of your real estate. You think about, he was talking about, somebody was talking about a new chip. I can't remember if it was I don't remember which one it was. 8 billion transistors on one of their chips. That's an infinite amount of transistors, right? Billions and billions of transistors on one chip. What are you going to do with all that real estate? Well, this is where they're spending their time, and a little bit of multi-threading. They put it all in multi-threading. So what they're doing is, when they come to a point where this thread is going to stall, they start another thread. When that one stalls, they start another thread. They start another thread. They swap back and forth. So they just don't stall, and they're using parallelism to fill those stall slots. And I forgot the point I was trying to make.